Hello everyone. I'm happy to introduce our speaker, Gilad Antler. Gilad is a PhD student at the Department of Earth Sciences, University of Cambridge, working on the isotopic constraints on the biogeochemical sulfur cycle. Gilad completed his master's studies with honor at the Department of Geological and Environmental Sciences, Ben-Gurion University of Negev, on multiple stable isotopes as a tool for studying the mechanism of bacterial sulfate reduction. Gilad was awarded by numerous prizes and fellowships, like Cambridge International Scholarship Scheme, Excellent Scholarship on the behalf of your CVP, a Master's Scholarship, Certificate of Distinct, and others. And Gilad published 9 papers in peer-reviewed journals. Please, Gilad.
Thank you. So, thank you all for coming. And today I want to talk about the coupling between the sulfur cycle and the iron cycle in an anoxic environment, and to show you how they are related to the carbon cycle. And the main tool that I'm using is sulfur and oxygen isotopes in dissolved sulfate. And I actually want to show you how by using these isotopes, we can see processes that we cannot see by using traditional methods. And the main question, or the big question, is what happened to organic carbons that reach to the sediment? So there are 3 possible fates to this organic carbon. One is oxidation, the other one is burial, or reduction to methane. And the question why, and this question is very important because we have 5 times more organic carbon in the sediment than in the entire ocean and the atmosphere combined. The entire, so the project I'm working on is the oxidation of the organic matter. And we know that bacteria can use different electron acceptor in order to respire the organic matter. And we as geochemists, we look at the pore fluid chemistry, and by the change of the chemistry, we can tell which process is happening. So first we have a reduction in the oxygen concentration. So we have here aerobic respiration. Then we have denitrification. Then we have a reduction of iron oxides. Now, in the case of the iron oxides, we look at the product, which is iron 2, because the iron 2 is soluble, where the iron 3, which is the oxidized form, is in the solid. Then we have sulfate reduction, and when we don't have sulfate anymore, we start to produce methane. Now this methane is going up in diffusion or in attraction, and it can meet the other electron acceptor, and they can oxidize it as well. Now, from all of this process, the most important process in today's ocean is sulfate reduction. And the reason for it, because we have by far more sulfate than all the other electron acceptors, in order of magnitudes more. So sulfate is the main oxidizer of organic matter in the sediment, in marine sediment, and it oxidizes roughly half of the organic matter. But also sulfate is the main oxidizer of methane and basically prevents from the ocean to become a source for methane because it's oxidized in the sediment. Now, if you look at the redox transformation of sulfur, we have sulfate as the most oxidizing form. This sulfate can be reduced into sulfide, which is the most reduced form. This sulfide can be reoxidized to sulfate. And in this process, we have all kinds of intermediates like sulfide, thiosulfate, elemental sulfur, and they both can undergo disproportionation to both sulfate and sulfide. And disproportionation basically means that the intermediate planes, the reducers and the oxidizer together, and the product is sulfate and sulfite. Now, everything that I just told you is very simple, but the real world is much, much more complex, because we have different interaction between different molecules. I'm not going to go over all this diagram because I don't want to bore you to death, but here you can see that we have the iron reduction and sulfate reduction, and the product is iron 2 and sulfite, and they can combine to FeS and finally to get pyrite. And in this process, we have net removal of sulfur from the system. But in the other case, this sulfite can be reoxidized back to sulfate. And then we have net recycling of sulfate. Now, the question if we have net burial of sulfate or net recycling of sulfite is important, because as you can see here, for example, this can generate, for example, the production of methane. And then if we are going in this direction, we can have a feedback, and a positive feedback that create more and more methane, and then we go into more and more reduced environment. And the big question is, why do we see in one place that one process is dominant, where in other places we can see the different processes dominate? Why, for example, if we're going to the Mediterranean and we're taking a core there, we're getting that one process is dominant, but if we're going to somewhere else, we see that another process. And the way that we are trying to attack this question is by taking cores and looking at, as I said, on the chemistry, but not only the chemistry. First of all, look at the core itself, and only by looking at the core we can tell a lot about different processes that happen there, only by the changing color, for example. And then we also can extract the water from the core itself, and then to look at the different chemistry of the core. So in here we use a system that called rhizomes, which we basically suck the water out of the sediment. There are different ways to do it. And if needed, we can do also incubation experiments. So as I told you in the beginning, the main tool that I'm using is the sulfur and oxygen isotopes in sulfate. And when I'm talking about oxygen, most of the time it will be the oxygen in the sulfate itself. So in sulfate we have sulfur and 4 oxygens. So just to make it clear. So in sulfur we're looking at the ratio between sulfur-34 and sulfur-32. And in oxygen we look at the ratio between oxygen-18 and oxygen-16. And then by using this ratio we define this delta notation, which is basically how different is the ratio in a sample from a given standard, and this ratio is in per mil. Now, if you look at schematic profile of sulfate reduction in the marine sediments, so here in black you can see the sulfate concentration. So the sulfate concentration is going down because the sulfate is being reduced, and the sulfur isotopes here in purple, they're normally going up. And the reason for it is because the bacteria preferentially take the lighter isotopes, so the residual sulfate become heavier. But for the oxygen, the picture is a bit more complex. So sometimes you can see that oxygen is also going up, very similar to the sulfur, like you can see here in red in trend A. But in other cases, we see that the oxygen becomes heavier very, very fast with depth, and then reach to equilibrium values. And if we cross-plot the oxygen versus the sulfur, we see that in the first case, we get a linear trend between the sulfur and the oxygen. And in the other case, we get a trend that's going into equilibrium. And a useful way to try to look at both of this trend, or to compare the trend, is by looking at the slope. Now, in this line, it's quite easy to look at the slope. It's basically the slope of the linear line. In the other case, what we actually do is using the slope of the inset, the beginning of the graph. So basically on the tangent of this curve with so if now we are zoom in into the process of bacterial sulfate reduction, and we imagine that this is our bacteria, So, and we have sulfate outside the cell. The sulfate is being reduced into sulfide in few steps, which involve few intermediates. And if we look at the sulfur isotopes, we see that the biggest isotope effect is during the reduction of the sulfate. So we have here big fractionation, and in the last step we have also big fractionation. But when it comes to oxygen, as we saw before, the picture is much, much more complex. And actually we have the isotopic equilibrium that we are getting is at the signal of the water, the signal of the isotopic composition of the water. But sulfate itself cannot exchange its isotope with water. And actually what's going on here, that sulfate is going all the way to sulfite, and then it can exchange its isotopes with the water. This exchange happens very, very fast, on order of magnitude of minutes. And then if this sulfite is going all the way back to sulfate, we can see these equilibrium values. So basically what I want to say is that we have here a tool to understand the amount of recycling that we have in the system. If we have sulfate that's going all the way to sulfide without reoxidation of the intermediates, we will get this trend A, that the oxygen and the sulfur are behaving the same. But then, if we have a lot of reoxidation of sulfide or of intermediates, we will get this trend that's going into equilibrium. Because we have this exchange with the water, and then we will see the isotopic composition of the water in the sulfate itself. And we demonstrated in the past that there is a good correlation between the slope of the graph between oxygen and sulfur and the sulfate reduction rate, which makes sense, because if the process is very, very fast, we assume that there will be less reoxidation of intermediates. But if the process is very slow, we'll get more and more reoxidation. By now, I talked only about bacterial sulfate reduction, which bacterial sulfate reduction is a process that we know very well. We know it from the lab, we know it from the field. We know which bacteria are doing this. We're able to isolate them. We know their biochemistry. But what I want to talk now is this process that's called anaerobic metanoxidation, which is basically bacteria that use sulfate and oxidize with it the methane. And the question is, how different are these processes, this bacterial sulfate reduction and the anaerobic metanoxidation? In both of them, sulfate is the oxidizer, and we're getting sulfide as the product. In both of them, there is oxidation of organic matter. But they are different. So first of all, they are different in the stoichiometry. So in bacterial sulfate reduction, we have the stoichiometry of 1 to 2 between the sulfate and the bicarbonate, where in anaerobic metanoxidation, we have a stoichiometry of 1 to 1 between the sulfate and the bicarbonate. So first of all, these two processes are different in the stoichiometry. The second thing, in bacterial sulfate reduction, we need only one bacteria to do this process. Yeah? And we were able to isolate them. We know exactly what's going on there. But in anaerobic metanoxidation, we have this consortium of archaea and bacteria, and this consortium is doing the oxidation together. And so we have different in stoichiometry, but we have also different in the organisms that are involved in the process. And the last thing, this is a very recent paper. They show that during the anaerobic metanoxidation, the pathway by which sulfate is being reduced is completely different than bacterial sulfate reduction, and actually involved with disproportionation of polysulfides. So the question is, if these two processes are similar or not similar, can we see it in the isotopes? As I told you in the beginning, we can tell by using the isotopes the different ways that sulfate is being reduced, the pathway by which sulfate is being reduced. So can we see it in the isotopes? And if we can see it in the isotope, what it can tell us about the difference between these two processes. And what I want to show you is result from two estuaries from the Alcor and the Kishon. One of them is just over here. And the reason why I really like to work on estuaries is because estuaries are the transition zone between the marine environment and the terrestrial environment. This has a lot of application because we're getting a lot of sulfate from the marine environment, but also we're getting a lot of organic matter from the terrestrial environment. So in very short core of 30 centimeters, we can see processes that in the deep sea we need to drill to 400 meters sometimes. And this is the sulfate concentration. So you can see that in both of them, the sulfate is going down, and after 20 centimeters, we don't have sulfate anymore. The profiles are not identical, but they are similar in many regards, especially if you take into account that the scale of this depth can vary between a few centimeters to a few hundred meters. But when we look at the dissolved inorganic carbon versus the sulfate, we see that we are getting different slopes in these two estuaries, where in the Archon we are getting a slope that is close to 1:1, and the Kishon we are getting a slope that is closer to 2:1, and then it changed to 1:1. And different slopes means different stoichiometry of the processes. So as I told you before, during bacterial sulfate reduction, we have a stoichiometry of 1:2 between the sulfate and the bicarbonate, which is fit to what we see in the Kishon. And in anaerobic metal oxidation, we have a stoichiometry of 1:1, which fits to what we see in the Archon. So basically, although in these two estuaries we see similar profiles of sulfate, the process by which sulfate is being reduced is completely different. In one of them, the dominant process is anaerobic metal oxidation, and in the other, the dominant process is bacterial sulfate reduction. And when we look at the isotopes, so this is the oxygen versus the sulfur isotopes, we see that they are completely different. And in the Archon, we are getting a slope that is almost twice as high than in the Archon. And to put it in context, I plot the results from the Archon and the Kishon together with data that we know from the literature. So I plot it here with data from Cold-seeps, where this is from the Gulf of Mexico, and this is places where we have a lot of methane that's going out of the sediment. Basically, anaerobic metal oxidation is the dominant process there. And also data from the deep sea where we don't have a lot of methane, and the dominant process is bacterial sulfate reduction. And what I want to say is that we have here a fingerprint for each one of the processes. Where in anaerobic metal oxidation, we're getting this straight line, and in bacterial sulfate reduction, we normally get these lines that go into equilibrium. So just to make it more robust, we also calculate the slope between the oxygen and the sulfur from all the data that we know from the literature. So we have here data from Cold-seep, Baltic Sea, and estuaries. All the data in gray is data from places where we know that there is a lot of methane. So it's all the Cold-seeps from both the Gulf of Mexico and even here from the Mediterranean, from the Baltic Sea, where we have a lot of methane produced, and estuaries. And we see that all the gray data are aggregate around the same number, which is exactly this unique isotopic fingerprint that I'm talking about. Where the data where we don't have anaerobic metal oxidation is much, much higher. Now this scale is a log scale, so small differences is actually quite big. And again, this is exactly what I'm talking about this unique isotopic fingerprint. That all the data from places that have methane aggregate around the same value. Now in Cold-seeps, we often find buildups of carbonates. The Nautilus were here a few years ago, and they found this thing even here in the Mediterranean. And this carbonate is being precipitated because of this process of anaerobic metal oxidation. But carbonates are not the only minerals that are precipitated there. There is also barite. Barite is barium sulfate. And we can take this barite and measure the sulfur and oxygen isotopes in the barite itself. So I haven't done it, but other people have done it. Here in gray, you can see the data from the pool fluids from all the places where we have a lot of methane. And the open squares, it's all the data from the barite. So not only that we have a unique isotopic fingerprint for the process of anaerobic methane oxidation, we also have a way to preserve it in the geological record as barite. Now, I don't want to dwell on this a lot, but I also need to explain why we are getting this unique isotopic fingerprint. The main problem with it is that we don't know this process very well because we are not able to isolate this consortium that's making the anaerobic methane oxidation. But if we give values for the fractionation for sulfur and oxygen from what we know from the literature based on other processes, we can do a sensitive analysis. And with the sensitive analysis, what you can see is that all the slopes that we are getting is of value between slopes of 0.2 and 0.4, which is very narrow range. Not only this, all this simulation, all of them give a linear line. None of them is given a line that's going into equilibrium. And the reason for it is that during this process, only one sulfate is being reoxidized for every 8 sulfates that's going into the cell. So, and this is roughly 10% of reoxidation, which is not enough to get a line that is concave to equilibrium. So to conclude this part, we found a unique isotopic fingerprint of anaerobic methane oxidation, which is different than what we see in bacterial sulfate reduction. We demonstrate that we can preserve this unique fingerprint in the geological record. And we think that this unique isotopic fingerprint is actually related to the pathway by which sulfate is being reduced during anaerobic methane oxidation. Now the second part that I want to talk about is the relationship between iron reduction and sulfate reduction. And for this, I'm going to take you to England, to the salt marshes. And this actually work that's been made by both me and Jennifer Mills, which is now in Imperial College. And this environment is very dynamic. This environment changes almost every day. And it comprises of a lot of components. We have here the vegetated area, we have here the ponds, and we have the creeks that bring water with the tide and drain the water when during low tide. And this is for the Hebrew speakers because in Hebrew we don't say salt marsh, we use the word milcha. And I think that the word milcha is not very good because in the Bible, this word is in bad connotation of a land that is very not productive and you cannot settle there. But the environment that I'm going to talk about is very, very productive, and you can see it by all the vegetation that is growing there. And the main salt marsh that we are working is here in Norfolk, is roughly 300 kilometers north to London. And we are working on the sediment from the ponds, which is roughly a pool with a diameter of 5 meters. We take sediment cores from the pond itself. And only by looking at the sediment, we can tell a lot about the different processes that happen there. So you can see that the very top of the sediment is very red. And then the sediment become black. And after this, the sediment become completely gray. And now if you look at the results of the proof fluid, this is the iron concentration. So the iron is going up. And it's going up quite a lot. It's going up to a concentration of 1.5 molar, which is people that work with iron don't use to this high concentration. Just to put it in context, we used to take the water out to put them aside, and after a few hours they become completely red because the iron got oxidized. Now the sulfate concentration, they actually increase with depth. But the sulfate to chlorine ratio does not change with depth, which means that the change in the sulfate concentration is not related to any removal or addition of sulfate. It's just mixing of either two water bodies or dilution or evaporation, because the sulfate and the chlorine change together, so the ratio between them does not change. So there is no net uptake of sulfate. And also the sulfur isotope does not change with depth. Now, if you take all of this finding and you give it to someone that is working on sulfate reduction, he will tell you there is no sulfate reduction in here, because the sulfate to chlorine ratio does not change, the isotope does not change, and the iron is increasing, which means that we are in the iron reduction zone. So sulfate reduction should not be thermodynamically favorable. But of course, if that was what happened there, I will not show it to you. But when we look at the oxygen isotopes, we see that they do change with depth. They actually increase. And this means that there is something here that activates the sulfate, but there is no change, or there is no apparent change in all the, basically in the mass of the sulfate. But also you can argue that this change might be because of the dynamic of this environment. It turns that this environment is very, very dynamic. It actually can be related to maybe two water bodies that sit one over each other. And we can see it. We can see that this change in the oxygen isotopes happens exactly where the sulfate is increased and exactly where the iron increases. So the question is what we see is real? Is it something biological? There is a bacteria that activates the sulfate, or we just see a mixing between two water bodies? So to answer this, we took the sediment and we incubated it. But we incubate it with unrich water. We enrich the water with delta 18. So if we see this enriched water in the sulfate, we will know that something is going on there. And to some of the bottle, we also add lactate, just to see what will happen if we'll add very available organic matter. So when we look at the sulfate concentration, we see that in the dead control, there is no change in sulfate, which makes sense. But also in the sediment with the natural condition, there is no change in sulfate, which makes sense because we didn't see any evidence for sulfate reduction there. But when we add the lactate, the sulfate got depleted almost completely after 2 months. And after the sulfate was completely depleted, we saw also increase with methane concentration. This basically means that the sediment have the potential to reduce sulfate, so the bacteria that can reduce sulfate are living there. And not only the bacteria that reduce sulfate, also the bacteria that produce methane. When we look at the iron isotope, so in the dead control there is a variation, but not a big variation. And in the natural condition, we saw an increase in iron, which makes sense. This is what we saw in the field. But when we had the lactate, we saw that the iron is increasing and then decrease. And the reason why the iron decreased because we start with sulfate reduction. When we have sulfate reduction, we produce sulfide. And this sulfide basically titrates the iron out, and we get this black precipitate. And now when we look at the isotopes, so this is the oxygen versus the sulfur, in the dead control nothing happened, everything is dead, so it's good. When we add the lactate, we see normal behavior of sulfate reduction. But in the natural condition, what we see is that it's a big change in the oxygen isotopes without any change in the sulfur isotopes, which means that what we saw in the field is actually real. It's not a mixing between two water bodies or whatever. It's a real process, and it's a biological process because we don't see it in the dead control. So there is a bacteria here that is doing this process. So someone is actively using the sulfate. Now you can argue that this environment is very crazy, but we actually see evidence to it also in in marine sediments. So this core I took it during my master. It's from Ayalon, the canyon of Ayalon. And the signal is much smaller, but we do see a change in the oxygen isotope without any change in sulfur isotope, exactly in the zone of the iron reduction. But the changes are much, much smaller. It's like order of magnitude of a few per millions, which is almost in our detection limit. But this process, there is a potential that it happens actually everywhere, not only in the salt marsh. And basically what we think that happened there, that we have sulfate. This sulfate is being reduced to some sort of reduced sulfur, and then this reduced sulfur is being oxidized with iron. Now this circle has to be complete, because we don't see a change in the sulfate concentration, and we also don't see a change in the sulfur isotopes, which means that we need to have 100% oxidation of whatever is being produced here. Now, near this iron-rich sediments that I just showed you, we see they're not really abundant, but we see also a sulfidic sediment. And the way that we can distinguish between them is by looking at the bottom of the pond. When we have iron-rich sediment, the bottom of the pond is very red because the reduced iron is diffused up and with the oxygen at the pond, so it's being oxidized just at the surface. And in the sulfidic sediment, we have sulfite that's coming from below, and this sulfite is being oxidized just on the surface. And one of the intermediates during this oxidation is elemental sulfur, which gives us this white field that you can see here. And the chemistry of these two ponds is completely different. So in one of them I just described, so there is no sulfate reduction, there is iron reduction, no sulfide, very small change in the dissolving organic carbon. But in the other one we see good evidence for sulfate reduction. We don't have iron because the iron got attracted by the sulfide, so we have excess of sulfide here, and major change in the DIC, the dissolving organic carbon. Also the isotopes, so I just described you the isotopes in the iron-rich sediment, so we don't have change in the sulfur isotopes, and the oxygen isotope does change, but this is because the process of this recycling of sulfate. But in the sulfidic sediment, we are getting a coupled change in the sulfur and the oxygen, which this is what we expect during the sulfate reduction. Now, interestingly, in the sulfidic sediment, we have also a production of methane, which we don't have in the other core. And when we plot the isotopes, again, we're getting these two ponds are completely different. In one of them we have active sulfate reduction. In one of them we have this weird recycling of sulfite. See that I have a lot of time. So just going back to this diagram, and now I want to talk about it in a bit more details. So basically what we think that in one of the cores we have net removal of sulfate. So we're getting all the way from sulfate. The sulfate is being the sulfate got reduced to sulfide, it's been titrated with the iron, and eventually we are getting pyrite. And as I said before, by the creation of pyrite we create hydrogen, and this hydrogen can react with the CO2 to get carbon, to get methane. And this methane can go and start this process all over again. So we have here this feedback, this positive feedback of creating pyrite, and then with this pyrite creating more methane going here and again and again and again, where in the other process we don't see it. We don't see creation of methane. We see actually recycling of sulfate, And in this case, we cannot produce methane because we have sulfates that being reduced to sulfide or to other form of sulfur and being reoxidized. And this keeps the sulfate concentration high. So if the sulfate concentration high, we cannot get into, thermodynamically, we cannot create methane. Not only is the sulfate concentration high, but we also don't produce high concentration of hydrogen sulfide and DIC to create methane. And we saw this only by looking at the isotopes. So only by looking at the isotopes, we can tell which of the processes is occurring, and it tells us a lot also of the carbon cycle. Because I have more time, maybe I will go to talk about the reason why we think that, well, something else that might mediate these processes, and this is the bioturbation. So in the iron-rich sediment, we don't see evidence for bioturbation. Sorry, in the sulfide-rich sediment, and this is because the sulfide is toxic. But in the iron-rich sediment, we see a lot of bioturbation. So you can see it here. This is the pathway the worm went, and also in here you can see this black trails of the worm. Not only this, we can see it in the chemistry. So if you look at the chemistry of the unreactive forms, like the chlorine or the delta O18 of the water, we can see that in the upper 15 centimeters, they does not change. They actually remain the same. This is because if we have something that all the time through the sediment, we expect to get here. We don't expect to see any change in all of these components. So even the thing that is not reactive should be the same, because we have something that mixes the sediment all the time. But this mixing also brings oxygen all the time. So the sediment become more and more oxic with time, which does not happen in the sulfidic sediment because we create sulfide. If we create sulfide, the sediment is toxic. We cannot start with the bioturbation, and we have this process over and over again. But if we are able to scavenge this sulfide out, the sediment is not toxic, and we create more and more iron oxides all the time by reoxidizing the sediment. So to conclude this, we found that we have decoupling between the oxygen and the sulfur isotopes in the salt marshes. We demonstrate that this decoupling is mediated by bacteria, and it's not something that's related to the dynamic of the salt marsh. And what we actually think that this recycling prevents from the system to become, to produce methane, because it's being reoxidized all the time. And with this, I will finish, and I will just thank you first of all for listening. I don't know if it was very boring or not. And obviously to all the founding bodies. Thank you.
Okay, thank you very much, Gilad, for your talk. Any questions, please? Yeah, please.
I have a few questions. The first one is, it's about salt marshes.
Mm-hmm.
What are the conditions that are making this very different pools or ponds?
It's a very good question because
because they are very close, I guess, or the same.
Yeah. So in the beginning, we saw that the aggregate. So we have places where we have a lot of these ponds that are very sulfidic, and other places where we have these ponds that are very iron-rich. But now we actually can find them sometimes meters apart. And it's a good question why they're so different. The truth is that we don't know.
Okay.
I think it's related to the size of the pond. And if you have a big pond, it's much harder to dilute so you have seawater that flushing everything probably once a month, because only when you have a springtime. But then when you have seawater there, the big ponds are much harder to dilute with rainwater. And then if you can dilute them efficiently, like you have small pond and you can dilute it, then you can, all the biology like it much more. So, I mean, but we don't know, this is the fact. So this is just an assumption. We're working on it right now.
Any other question?
Okay,
Okay.
Okay. And so if you are talking about the scale of your water reservoir, water body, so when you compare salt marshes or estuaries to the open ocean, and I'm not sure exactly what's my question, but I want to understand what is the connection between the amount of organic material that is being deposited on the seafloor and the rate of the diagenetic processes, because in this more coastal and shallow water environments, you have much more organic material than in the ocean. So it's
well, yeah. So first of all, in theory, it should be related, obviously, but the dependence is not one-to-one. So it's not as simple. We don't. So this is, as I started, is our outstanding question, because we cannot correlate, for example, the TOC with the rates of some of processes, because the TOC is comprised of variety of organic matters, and we don't know to separate them very efficiently. There are people that are doing this, but they are able to measure like 20,000 different molecules and still not getting 100% yield of the TOC. So we don't know a lot of this TOC. We're doing this generic measurement of TOC, but it doesn't necessarily tell us something about which is the reactive organic compounds. And I think that it's not only the TOC, it's the entire fabric of the sediment. So we have the TOC, we have the amount of iron. Yeah, so in places like the Mediterranean, we have much more iron than in other places because of dust. And it might be related to something else that we are not taking into account.
So, and did you try to, like I saw in your experiments, that the scale of time is days.
Yeah.
Do you have an estimate of what is the scale of the rate in the natural environment?
Yeah, well,
because you added the organic material at the you know the amount.
Yeah, but even when we didn't add the organic material, we still saw changes on the scale of weeks. Okay. As I said before, this environment is very dynamic. Not only is it's very dynamic, it's very, very easy to change it. Like you add a bit of organic matter and you change it completely. So it has a lot of application, not only for the natural environment, but also, for example, in England, they really care about management of the salt marshes. And if you add a bit of organic matter to the salt marshes, like by farms that drain their nutrients into the salt marsh, you can very easily change the sediment from iron-rich sediment to something that starts to produce methane. And we know that salt marshes are not a big source for methane, but it's very easy to convert it from not producing any methane to produce a lot of methane.
And are there, if you're saying about production of methane, are there any industrial applications for producing methane this way? Or?
Well, this is not my part, but I mean, obviously we don't want to produce a lot of methane, so we want actually to produce less methane. Yeah, I don't know if this is the question.
I'm trying to understand if this is something that is being used not only for pure science.
Well, I'm trying to put my hands right now away from all kind of geoengineering, but I assume, I mean, there are a lot of applications to this, mainly on the carbon cycle.
Yeah.
From both the methane point of view, but also from the CO2 point of view. Because these things, I'm showing here the methane, but it's have a lot of application to the carbon itself, or to the CO2. And the salt marsh, as it is right now, it's a sink for carbon.
I know, yeah. I think wetlands and saltlands are a very important reservoir that is buffering or controlling CO2. And so I think there's a lot of interest in that.
I'm coming from more geological point of view, but also salt marsh have application in the past. So we think that there were places in the past where we had more salt marshes, and they might change the entire carbon cycle in the atmosphere. Or I don't know if it will.
No, we have time. Okay, so two quick questions. First about the marshes. Do you see any other elemental changes along those profiles other than the iron and the DIC and the sulfur?
Yeah. So I assume that you are going to the calcium.
And not necessarily calcium, manganese as well.
Yeah. So there is not a lot of manganese in there. So it's probably 3 orders of magnitude less than the iron, which is still quite a lot because we have a lot of iron, but it's probably not plays a big role there. We don't see change in the calcium in both of this.
And how about silicon?
I don't know, we didn't measure.
Okay. And the other question is,
but on the nutrient cycle, it should be very interesting there as well. So it's a big effect.
And the second question is, you're talking about primarily advective environment that are organic rich sedimentation with low sedimentation rates and with not where you can recycle a lot of sulfur. So have you looked at comparable marine environments, specifically stuff that's in the middle of big oceanic gyres in brown shell faces?
Well, the results are similar. I'm trying not to be a bit more conservative in here, but the results, like the iron-rich sediment that we are seeing, is very similar to what we see in the ocean in the big gyre, where we don't have a lot of organic matter. We think that we see the same processes there. It's much harder to study it there because you need the ODP to go there to take course for you. Where in the salt marsh we just take a car and drive for like 1 hour and take it with our hands. But we think, we don't have a lot of results, but we think that the processes are comparable.
Okay, other question, please? Okay, so I have a question, probably not related to your talk. So what is the reason that in the marine sediments, the anaerobic oxidation is much stronger than in the lakes? The anaerobic oxidation is much stronger than in the lakes?
In lakes?
In lakes, yes.
Well, there are 2 parts for my answer. The first one is most of the lakes are terrestrial environment. So in terrestrial environment, you don't have a lot of sulfate. So if you compare the ocean, we have 28 millimolar of sulfate. And if you take let's say Lake Kinetic for comparison, we have 100 times less sulfate than in the ocean. Yeah. So you lose this ability of sulfate to oxidize on the methane because you don't have a lot of it. The idea that with sulfate in the ocean we have so much sulfate that it can oxidize is the main oxidizer. But in terrestrial environment you don't have it anymore. Now I'm not sure what's going on in lakes that are more salty. But anyhow, in the sediment in marine sediment you have the sediment itself, and the entire process is happening in the sediment where sulfate is being diffused into the sediment. So the process, it can allow the process to be much slower in a way. Yeah? Because you have methane that's going up in diffusion or advection, but you have the sediment that prevent it to burst up. Where in lakes, you normally don't have it. You normally have production of methane that's going up straight away.
Okay, thank you. Okay, thank you very much.